clear, yeah, of stable maps, yeah.
So what roughly is the condition of the nodes?
So you approach including derivatives up to order 3 with a certain exponential decay the image of the node. So if you take holomorphic polar coordinates and view, if you delete the node, view it as a cylindrical end. Once you run to the infinity, you approach this image of the node with an exponential decay. Yeah, for the Fredholm theory. So what you ultimately have is, if you remove the nodes, you have a Riemann surface with cylindrical ends, and the Cauchy-Riemann operator would have the structure. If this is the S direction and this is the T direction on the loop, it would have DDS equals J of at the infinity J at the nodal image. Once you fix a almost complex structure, D dt. This is a self-adjoint operator, so you would have, so the structure of the PDE is you have a self-adjoint operator which has a kernel, and you go to this, and so yes, but the coordinates which you take for this is DDS on the cylinder, and you have asymptotically a self-adjoint operator sitting, and the self-adjoint operator has spectrum 2 pi z, but also 0. So 0 is in the spectrum. The reason for this is that you have to view the nodal point as the as a constant loop. And the whole manifold is a family of constant loops. It's a Morse-Bott manifold of loops. And so since it's Morse-Bott, you have to put that decay. Otherwise, you don't get a Fredholm problem later on. So that's one of the reasons. I could do it without weights here. And I could definitely define a smooth structure, but it wouldn't work very well with the Fredholm theory. So now, so in order to define this, I had a symplectic manifold. And now let me make an auxiliary choice. J is a compatible, almost complex structure on Q. And compatible, of course, means that this is a Riemann metric here. So now let me define another category, E. And E has the following objects. So tau is the same than that. Yeah? And what is psi? So for Z in S, psi Z goes from the tangent space to the Riemann surface at the point Z with a complex structure to the tangent space at U of Z Q and is complex antilinear. So, and I have to say more about it, what's the regularity. So the psi, so the tau consists of SGMDU, and the psi is for every point in the Riemann surface a complex antilinear map from the tangent space of the Riemann surface at the point Z to the tangent space at U of Z at Q, and it has the following regularity. Is in H2 log away from the nodes. And now I have to say what it does at the nodes. We take our remember we took a chart near the node to say how the U behaves. I take the same chart. Then I have U. I take the same holomorphic polar coordinates. Then I can so then I feed in here. So this here is I can feed in d sigma ds of st. So I take the partial derivative with respect to the s coordinate of my holomorphic polar coordinate. That gives me a vector in the tangent space of the Riemann surface. I feed that into this complex antilinear thing. That gives me a vector in the tangent space. Then I transport it as R to n and take the fiber part. And this is weighted with E delta S, delta 0S, in H2 so here's only twice differentiable. So these are okay, so psi was this chart which I took at the end. Remember when I defined what the property of u at the node was. I took a chart psi which maps the neighborhood of the point u of x. X was a nodal thing into R to n. And now I just take the tangent, takes the same chart, takes a tangent. So what it says is that so in particular psi over the nodal points is 0. But nearby it goes exponentially down, including its derivative, up to order 2. Okay, so now we obviously, by construction, have a map that's a functor. So it's clear what isomorphism here means. Isomorphism between two such objects means, of course, that phi, so it looks like morphism here is tau t phi tau prime, and then there's an underlying morphism which you have already seen, this one. So this one is between the objects, and so two things are isomorphic provided the underlying object, the tau object is isomorphic, and you require that psi prime composed with t phi is psi. So now this defines what morphisms here are. So the underlying stable map is isomorphic, and the isomorphism which you use, if you take the tangent of this biholomorphic map, should relate the psi's in this way. No, psi is, well, 0, 1 for TQ valued 0, 1 forms. It's not the variation of the object U. It's another bundle. And it's clear. So two objects tau prime are isomorphic provided, and the isomorphism has this form. So the underlying thing to T phi is phi. That should be an isomorphism between the taus. And the T phi should relate to psi and the psi prime. So now then this is a category, and you have a forgetful functor. Yeah, there's a bundle here. It's a functor. And then, of course, the nice thing is that we have a functor as well, namely, so let me write this here, Sjm du is Sjm du 1/2 Tu plus j composed with 2 little j. Yeah. Infinity, C infinity. D sigma by dt. Yeah, because it's holomorph. Yeah, should be true. Yeah, then you have just an I there. So ultimately, what I ultimately want to say is, this is something like a smooth bundle over a smooth structure of this category. This is a smooth functor. This is a smooth section, and it's also Fritton. And want to have some kind of perturbation theory compatible with the structure which I have on the category. Of course, the description would be that there's, of course, a lot of junk in the category, which is just that there are so many isomorphisms, so many objects, but transversally, because the orbit space is the orbits class, when you divide out by the automorphism, is actually a set. It just says that you have a lot of, that if you look at the space of slices there, in some sense, that's a set. And that is how you want to define a smooth structure, by taking sort of slices. So yeah, okay, so an element here is a tor, which is just this thing here. And then this here is tor, and that is the psi. I mean, there's a particular psi, which you produce out of this data here. Yeah? You take the tangent, you just make it complex antilinear. You make the tangent of u complex antilinear. So remember, u was of class 3 delta 0. If I differentiate it, takes a tangent tu, the best you can expect is 2 delta 0. So then this, and then you make it complex antilinear by this thing. So that will be, in fact, at least formally that makes sense. So, well, you can multiply the sections by j, and it would still be complex antilinear. So there's a complex structure. So yeah, let's look at the structure of this thing. So over each object, there's a Banach space. Yeah? So the pre-image of an object is actually a Banach space. The space A of H20. And that is, in fact, a complex Banach space because it can multiply by I, just multiply by j of u. Okay. So now, let me here, as a side remark, in SFT, you would have a similar picture. You have a category of stable maps, but now the stable maps are defined also on punctured Riemann surfaces. And they are, besides nodes, you have punctures, where the image of a holomorphic curve would approach a cylinder of a periodic orbit and so on. But you still can talk about stable maps. And the interesting thing is that in this case, there is something like, there exists something like two functors into some other category. In fact, what this is if you have an object in SFT, then there are positive asymptotic periodic orbits and negative asymptotic orbits. That defines your functor in some trivial category. If it's more spot, it's a little bit more complicated. And then you can define a Feilbert product, which is sort of S and it also lives up to the bundle. These are objects, these are broken things, like in Floer's theory, where the positive limit is the positive limit is the negative limit of the other one. It's like a matching of gradient lines. And then you can, if I can define what a smooth structure means in the category, and I could define what a smooth structure with boundary and corners would mean, I could talk about the boundary of a category. So now in Gromov-Witten there is no boundary. But in the other, in the SFT category, there will be a boundary, and there will be some kind of a concatenation map, which is some kind of a covering. One would have to say what that means. So you would have this relationship, and this is some kind of functorial relationship between a certain subcategory of S and the other, and it would live to the bundle, and the Cauchy-Riemann operator would be compatible with this. And the whole algebra of SFT comes from this structure and some other things you can do in this category. And you can formalize whatever you can do, and it's important on the level of category, forgetting what nearby objects are. So there are a lot of functors, yeah? And the Cauchy-Riemann is compatible with this, and so on and so on. And what you want to say is I can put a smooth structure on this, and whatever I'm interested in is actually a smooth operation. And then you make a perturbation theory which keeps all this smooth, which respects all the smooth perturbations, which of course in general you can't do without multivariate perturbations. So you have to talk about weights and so on. And so then if you it makes a huge amount of difference when you have so many moving parts, when you have a nice structure for the objects, and you can think of, and you don't have to make ad hoc constructions. Yeah?
Go back a little bit. You said that three-dimensional objects are only finite-dimensional.
Yeah.
Can you give us an example where there's more than one?
Well, if you have the two-sphere with a constant map on it, you can take all rotations on the two-sphere. So take the two-sphere, so Riemann sphere, and just U equals the constant map. Then all Möbius transformations are automorphism. Infinitely many. Six real dimensions. Oh, are you asked for stable and more than? Yes. So, for example, if you have, so for example, take a map from the Riemann sphere into something and compose it with z goes to z squared. Then you have already more. And then so take a non-trivial map into the, say a map into CPN into the non-trivial class from S2 into the class of CP1. Just the embedding, let's say. And now, but now compose, go from S2 to S2 by z goes to z squared, compose with this map. That will have now at least one, two, besides the identity, another automorphism. It's the biholomorphic maps between the Riemann surface, so that U prime composed with phi is U. Okay, so now this is all overview, but one should keep this example in mind. You want to be dealing with this kind of problems, and want to add some structure to this, so that once you added the structure, that there's a whole abstract machinery which say produces invariance and so on. Okay, so now recall the difficulties which I described at the beginning. They all will occur. And so when I now talk about polyfolds, so there are actually a certain number of things. So there are several parts, actually. It goes back to calculus. So we have to look at calculus again and see that out of the infinite dimensions, you don't have any choice. Calculus is calculus. But if you go to infinite dimensions, the preferred choice was a very specific one, Fresher differentiability, and that doesn't work with all the things which happen here. There are, in fact, infinitely many choices. There are some which are rather straightforward and some which are not that obvious. So once you introduce a new way of doing calculus, you can immediately do geometry, provided you have the chain rule. Yeah? So any good notion of differentiability should, of course, involve something like the chain rule. So there's calculus geometry and nonlinear, and some kind of nonlinear function analysis. So I think everybody knows what linear function analysis is. There's a similar thing called nonlinear function analysis where the operators are nonlinear. Yeah? So once you have this, so all this comes hand in hand. Yeah? So you could, if you generalize calculus, you can, in principle, you can say something new to the things here. So this is abstract nonsense in some way. Yeah? And then, of course, you have to deal with concrete problems. So if I tell you what an abstract smooth map is, and then I send you out in nature and say, look at this map, is that actually smooth? It's not so clear if you know if it's actually smooth or not. Yeah? So there's something which I would call nonlinear analysis. It tells you that certain things which happen in real life are smooth maps and so on. So like PDEs and certain things. So this abstract nonsense, this is more concrete here. And then at the end, I call it black box theory. So this is again abstract nonsense, but it is something like you give specifications how to do certain analytical constructions, and there are certain regulations what you have to do. It's like at the end you give you prove a certain construction if it adheres up to certain standards you impose, and then if different people make these constructions in this framework, you can bring these things together, and the abstract nonsense tells that they will work together. The advantage of this thing is that you can recycle analysis. That is one of the issues in our field, that analysis is always recycled by saying, well, we can do it as in this paper, which then refers to something in a very large paper, which is then you take a bit out, you put it into some different context and claim it works. Of course, if you check it, it's painful because you have to say how it works with the other pieces together. But if you could package the individual pieces so that automatically you would know if you can put them together, they work together. That would be very helpful. So that is what we want to do here. And it's like this. So if I say I want to construct smooth structures on a category. Okay, so how do I do this? So I even have a problem if I have to construct a smooth structure on a topological space in the usual way. If somebody gives me a topological space, put a nice smooth structure on it. Wow. So how do we actually define smooth structures? We construct a certain number of good models, and then we invent certain constructions how to modify them. So the same is here. Our categories in general are the objects in this category are objects which by itself have a structure. Like in our case, we have a Riemann surface, map on it, nodal points. You can cut the Riemann surface into smaller bits, and you can make constructions for the smaller bits near a nodal point, and so on. That gives you a black box if properly packaged. And then you make for the other things, and if you can glue that Riemann surface with that Riemann surface, the situation, then you get a bigger object, and it also would be covered by some theory. So that is what I mean here. It's also a tool how smaller bits can be put together. So from the stuff I'm talking about, so so the last paper we wrote was doing this polyfold theory with Gromov-Witten, but when we do this, this is a long paper. We do this it's written in a graded book style, so I think there's basically everything there is spelled out in detail, or referred to things where actually things have been done. So now in this case, we use some ad hoc. I would say it's ad hoc. So now what we're currently preparing is a paper where we take what we did there and package it in small black boxes. And we get 2 black boxes out of this. And then the next thing is the SFT paper where we where we construct a third box, and then we use this theory of putting them together and get SFT. So that's how it will be done. It's of course always good if you work with black boxes to at least understand what happens in the black box in certain cases. Have at least some idea what's in a black box. So therefore, when you do this more with ad hoc in this polyfold stuff with Gromov-Witten, that is how ultimately you would not do it. But it's good to see what it is, and then you repackage it into these black boxes. And then if you know, and the black boxes actually is a nice formalism. So a black box looks like this. So at the end, the thing is, it looks like this. No, just saying. So this would describe, this would describe a space with a bundle over it in a section, would be represented by this thing. And if you would have another one, where it happens, that this thing looks like this. No, just then you can glue these 2 things together and you get a new black box. which would look like this. And then, of course, you can contract this, would be another looking black box like this. And if you have some other structure and at the end is no end back, you have a Fredholm problem. So that is how it ultimately will work. And for Gromov-Witten, there are actually two such things. You can put them together, and then out of this you build Gromov-Witten. And for SFT, there is an additional one which looks like this. And you have to use this kind of thing several times, depending how often it's broken. Anyway, okay, so I'm sure it's not helpful, but there was I had to say. The formalism is that this is covered by mathematics. It turns into graph theory at some point. Okay, so graph theory with funny colored things. So now, calculus. So it starts actually quite boring, and it is known to people in linear function analysis who study what is called interpolation theory, but they never interpret it in this way. So let's make the following definition. So let be a Banach space, then an SC structure on E is given by a nested sequence of Banach spaces. So that means I have subspaces, but they have stronger norms on them, which makes them into Banach space. So that this inclusion here is bounded linear operator, and E infinity is dense in every EM. So, for example, the Sobolev scale, yeah, so, no, bounded at the moment. So now the scale is called compact. So I want to recover also usual differentiability. SC scale. So that is what they call in interpolation theory a scale. So now an SC structure is compact if all are compact operators. So it actually turns out that this is where all the new stuff happens for these scales here. So now you will see in a minute or so, you will see that this gives you the notion of a smooth structure on the Banach space. Yeah, you presume it could also do some continuous thing if you want, but I know, but I understand this, but
So maybe then you could understand how to get closer to the C0 category by looking at some Hungarian C outputs.
yes, but I'm aware that one could do this, but I wanted to do ultimately SFT and just keep. I mean, it's already complicated enough, but you can definitely play around with this thing. So now, it turns out that the SC structure is actually the notion of a smooth structure, and then, as you will see, interpret it properly, and then the particular structure E will be the one where you get Fresher differentiability, the usual generalization. Then, and then it will turn out that for this, where these are compact operators here, the inclusions, that there are some really interesting things happen, which in fact lead to this new space, new even finite dimensional spaces. Okay, so now, so let me write if A is a subset of E, I write AI to be. Of course, in this case, if A is stupidly chosen for large I, that might be empty. But if U is open, it will not be empty. So then, you can also define the following. A upper M, and A upper M is just AM with a structure AM yeah. Yeah, so, I mean, as I said, this can be for E large empty, but if A is, for example, open, then AM would be, you start with this space and take just the tail end of the filtration. So now, then it's clear what is, suppose this is linear. A linear C operator would map EM into FM and should be continuous as such. Yeah? An isomorphism there is one which is invertible, and also the inverse is an SC operator. So it's clear what the linear algebra here is. Then let me now define what a partial quadrant is. So some people also call this a sector. So a partial quadrant is C is a convex set, so that there exists an SC isomorphism T from E to Rn plus W. So this is clear what an SC sum is. Yeah, you have two spaces with an SC structure. Take the thing and takes the diagonal filtration with T of C equal 0 infinity in W. Yeah? So something which you can bring to this cone-like thing here. So now, let me first say that there is, of course, a completely stupid way of generalizing differentiability, which I would also call that a map, in this case, I would say a map is Cj. If it's if it maps each level into, so it preserves the level, it goes from FM into, or EM into FM, and it's Cj there. Then in the case where you take the constant structure E, that would be pressure differentiability, the usual one. This is what? Oh, this is SC. So this is an SC space here. Rn only has one SC structure because of this density requirement, Rn, Rn, Rn. So this has now a diagonal filtration, which should be preserved. So if you have two, no. So if you have two SC structures and a linear operator maps then EM into FM, and there's a bounded operator there. Bounded, yes. So it may level into level, and it has to be bounded there. So here, a partial quadrant is just a particular convex set, which essentially looks like this quadrant here with. Yeah, well, I would call this a quadrant. Partial because I have still something hanging here. I mean, some people call this sector. I don't know what they are. We call it partial quadrant, and we call it ever since, and nobody ever complains. So. Okay, so now, so there is an obvious notion of being Cj. So if you have U in E and you go into F, then you would say that F is Cj. I don't want to introduce more notions of differentiability, so I would say J if F goes from Um into Fm is Cj for all m. Yeah, so it preserves the levels and is Cj like this. So this is obviously the straightforward generalization of the usual notion of differentiability. Yeah? So if your SC structure is the constant E structure, this is just usual Fresher differentiability. Yeah? Yeah, so for every m, this is Cj. Cj is the usual differentiability. The Fresher differentiability. So I'm just saying, we know what Fresher differentiability is. So I say now the really trivial generalization, if you have such a scale of differentiability, is just it preserves each level and is Cj there. So it's clear what kind of theory you get. It's not particularly exciting, a little bit stronger in general than if E is equals constant E. But notice, at least at this point, that all structures you put on function spaces, they usually are defined via the exponential map. So if you, for example, put on the Sobolev on the space of Sobolev maps of class H3 from the sphere, two-sphere into a manifold, this filtration, then the usual charts, which used by exponential map, will preserve the other things as well. So the charts are usually then, for basically any reasonable filtration you take, Cj. But what we want to do is we want to define a not so obvious notion of differentiability, and which comes now. So here's the definition. Oh, and presumably this time I have to stop a little bit earlier because let me stop in 10 minutes. Yeah. So then I think the net result is 2 hours for the morning. So okay. So definition. So E is an SC-Banach space, C is a partial quadrant, and U is open, relatively open. So now, and assume you have the same here. Yeah, so we have U and V, which are relatively open set in partial quadrants, and F. So that I use this relatively open in C rather open sets in E has that I want to ultimately construct things with boundary and corners. So now F is SC1. That's a new notion of differentiability scale, SC scale times, in the scale sense, one time differentiable, provided the following is true. F is SC0. This is just continuous in this thing, which means it preserves the levels and it's continuous on each level. Secondly, for every x in U1, there exists a d of x, a bounded linear operator from E0 to F0. So these are the original spaces, the Banach spaces E and F. so that the limit of h so you just take the limit over h goes in the one norm to 0, but of course you have to make sure that x plus h lies in u is of course efficient, of 1 over so it looks like the usual definition, in some sense it is, but you have always to look for the norms. The 0 norm is 0. So if you make changes on the 1 level, and then you just look at the end result on the 0 level, divide, it goes to 0. So it means at this point the map, if you go like this, 1 level down, it's differentiable. So then 3 if I define, so for xh in u1 plus e, define tf of xh, which is f of x df of xh. So let's observe that for this point this is defined. F of x is obviously defined and is a point on level 1 because f preserves the level. X was on level 1. F of x is on level 1. Then d of x was defined. Is a bounded linear operator on level between level 0. So this is defined. Then tf from u1 plus e into v1 plus f is SC0. So if you define this is SC0. So actually, let me write like this. This is a space shifted by 1. So the filtration is here. The 0 level is U1 plus E. The 1 level is U2 plus E1. And then if for every m, so that is not compact, means it's not a compact operator, the map, so you see here, since this preserves the levels, it maps the df of x. If x is on level m plus 1, then this would map h on level m to level m. So therefore, you can at least look at the following expression. So therefore, if x is on level m plus 1, then the df of x is in fact a bounded linear operator from here to here, but you require this to be continuous as operators. Yeah? So this is vacuous, this condition, if the scale is compact. So by this condition here, you know if the point x lies on that level, on the m plus 1 level, then df of x maps em into fm and is a bounded operator. So you require that if you vary x on that level, this bounded operator behaves continuously as an operator. But this is only in the case if this is not compact. So now at this point, let me make the following definition. You see this thing appearing here. And the definition, which is I will make, is that Tu so in particular, Tu, the m level, is um plus 1 plus em. And I call this a tangent of U. So with this definition, this here is in fact TU, and this is TV. F, yes, sorry. So if we use this definition here, then TF is actually the tangent, would be the tangent. And that is our notion of differentiability. And note, if the scale is compact, this doesn't occur here, number 4. Yeah? The purpose of this is that I have a theory which also contains Fresher differentiability. So if you take the scale E, then this here is a complicated way of saying the map is Fresher differentiable.
Is there a reason you want a theory which contains Fresher differentiability?
Yes. I want, when I do Fredholm theory, then there are these areas where the domain actually changes, which is bad. But in other areas, the Cauchy-Riemann operator on a good part of the domain is actually nice, and it's actually a classical operator. And the classical operators have certain properties, like if you take a C1 small perturbation, they still stay Fredholm. And you can talk about a C1 small perturbation in a certain area, but not in other areas. So you want to have that.
But presumably, you may also develop something similar for Gafford.
So the difficulty is actually, and it barely makes it, you have to work for a while, is the following theorem. Yeah, let me, otherwise I'm running out of letters here. So these are not dual spaces. And if F from U into V and J from V into from V prime, U into U prime, V from U prime into U double prime are SC1, then G composed with F from U into U double prime is SC1, and T of G composed with F is T G composed with TF. So in other words, a chain rule. So it's not so apparent because, so first of all, what this means here, you have a nice approximation if you lift the index by 1 and go 1 down. So now you would say so maybe you work a little bit and you can show that, and this is only from level 1 to level 0. So it turns out if you work on this condition, you have the same approximation property from level 2 to level 1, and so on. But this is already a theorem. So now you would say, if I now take 2 of those guys, then going for the first map down by 1 is C1, and then I have to go by the second one down again. So in the composition, I have to go down by 2, yeah, in order to conclude that that is differentiable. But it turns out, no. It turns out that for the composition, still going down by 1 is sufficient. So it's not that obvious. So you really have to work for this. So you still have the chain rule. So now let me give you some consequences, and then we have a break here. Or maybe before the consequence, let me just draw let me just say the following, then after lunch we continue. For compact scales, C structures on E, there are interesting So it's clear what higher differentiability means. Higher differentiability means that the TF is SC1. That means then the F was SC2. Yeah, so inductively it's clear how to define this. There are interesting SC infinity maps R from U into U with the property R composed with R is R. And I have to say what interesting means. So this thing are called retractions, so this would be smooth retractions. So it's a little bit of an exercise. If you take standard differentiability and take a smooth map, Freshy differentiable, which has this property, you can show that the image of such a map is always a submanifold in the Banach space. So if R is C infinity, so Freshy differentiable, then R of U is a submanifold. In the usual sense that you can construct a chart which makes it straight into a factor of a product. Now, if you have this compact scales, it turns this result is not true. There are interesting retracts which are not manifolds in any way, which are smooth retracts, namely in R plus L2 of R with the following structure, with the SC structure. R plus HM delta M of R, where delta 0 is 0, less than delta 1, less than delta 2. So what I look at the Sobolev space HM, but with an exponential decay at infinity given by this weight. So now, so Sobolev embedding is compact on bounded domains if you go down in the derivatives. But since I put this stronger and stronger weights at infinity, there's no lack of compactness at infinity. So this is an SC, this is a compact SC structure. Then on this space, E, on E there is a SC infinity retraction, R, and R has a form, R of TU is T pi T of U, where pi T is from L2 into L2 is a projection. So that the image that R of R plus L2 is actually is homeomorphic to this thing here. The half line, this point, this excluded, and here's the open half space. So there are smooth retractions which retract R plus L2 of R onto something which is homeomorphic to a half space, open half space with an with the half line attached. Yeah, so that is an example of a polyfold. So now it turns out there's an easy formalism where you will see that you can take as a new models for smooth spaces the images of smooth retracts. So this then gives you already a local model of a transition from a 2 to a 1-dimensional space. So for example, this thing here then is a manifold in this category already based on that example. But I have to explain a little bit now how we use this as local models and so on. But so the interesting thing is that for this more general notion of differentiability, you get really much wilder spaces which are retracts. And this library of retracts is so large that you can model all this phenomenon like bubbling off and so on. And you need this. Yeah? Oh, yes, okay. So So, okay, so E is R plus L2 of R. Then E1 is R plus the Sobolev H1 with a weight delta 1. R, and then E2 is R plus H2 delta 2 of R. But you can really have fancy things, like you can start, say, with E equals C of omega square. Then you take E1 to be C alpha to make him happy, and then you take E2 to be Sobolev space, I don't know, suppose it's bounded domain H300 of omega square if the dimension is not too big here. And this would be a scale, and then you would have that the tangent of E on the first level, on the zero level, would actually be C alpha of omega square plus C of omega square. So alpha, yeah, here would be a fixed alpha Hölder thing between 0 and 1. Yeah, so you can really have wild combinations of all spaces as long as the inclusions are compact. And I don't know if I can construct the strange retractions there, but in the Sobolev space, you can do this, and then of course you can take direct sum, use the fact that Hilbert spaces, if they're separate or isomorphic, so you can construct this example with a lot of varying dimensions, and you can also construct things where you start with some infinite dimensional stuff, and then it's something finite dimensional. And since you ultimately can do a Fredholm theory on this, you could start with an infinite dimensional problem, then the infinite dimensional problem gets finite dimensional and becomes a combinatorial problem, and it's covered by a Fredholm theory. So this kind of things are possible in this language, yeah? Yes, before lunch or after? Yes, I just wanted to make sure that you are the culprit here. Yes. No, it's not complicated. So, oh, no, it's getting more complicated because I'm losing things here. So, just take compact support and integral beta squared equal to 1. And now define, so remember that our R of Tu has the form T and a projection. So we define pi t to be 0 for t less or equals to 0. And we define for t positive pi t of u is the integral of beta shifted by E1 over t. So you see if t goes to 0, this thing whooshes to infinity. Times u ds, and then so then it involves a certain amount of calculation that thing is actually smooth. This thing, in a sense. So you see that up to time 0, including time 0, the projection is 0, and then it's a one-dimensional projection. But you see what happens is that this thing weakly converges to 0 if t goes to 0. Just goes away. And then the fact is that this is, of course, not smooth preserving the levels, because then it's a theorem that if it preserves the level, it would be level-wise smooth, that the image is actually a submanifold. But obviously it isn't, because it changes dimension. So it's actually important that the differentiability involves something going down, a relaxation like this. What pi t is a projection. Pi t is a projection. Oh, sorry. Yes, this what looks like injection is actually projection. Okay, so that is this example. So it's unfortunately complicated. Then another thing which becomes smooth. So let me just say that as well, and then we have lunch. If you take the same structure on R, which I defined, the shift operator. So here we take the same, so this Sobolev spaces with weights, and here this is now is SC infinity, but it's not C1. So this thing is now smooth in this category. That resolves some of the issues. So in particular now, lunch, yes. So if you take our space before of curves, the curve space, now the R action is actually smooth. So it actually turns out that the quotient space is actually a smooth manifold in this in the SC category. The space of spars divided out by R has a smooth structure in this sense, where it locally looks like an open set in an SC space. Okay, lunch. So I wanted to stop at 20 past, but this is his fault.